Welcome back to part 3 of our video series here dealing with the vapor-liquid equilibrium. So now that we have wrapped up talking about the bubble pressure and dew pressure and bubble temperature and dew temperature, what we're going to do in this video is deal with the situation where we have a separation process happening and the concept of the flash calculation and how we can solve the flash calculation using the Rachford rice as the calculation that we'll derive for the flash calculation here. And what is going on with this situation here is we have a flash drum, and for our flash drum we have a feed. Now this feed has a certain composition that we know going in, and in this case we'll say it is 0.4 of benzene and 0.6 of toluene, and this will be our Z1, this will be our looks a little sloppy there, Z2. Now, so we have our feed coming in to our flash drum. What's going to happen here is the feed, whatever the feed is, it could be 100% vapor, it could be 100% liquid, it could be a combination of the two going in. It really doesn't matter. What matters is the fact that it is going to separate inside the flash drum into the liquid phase and the vapor phase. And out the top of our flash drum will be a certain mole fraction amount of vapor that is leaving, and in the other side of our drum will be a certain mole fraction amount of our liquid that is leaving the flash drum, which then leads us to say, how do we know what the amount that is going to be in the vapor phase, how do we know the amount that is going to be in the liquid phase, and then what is the composition of both of those phases? So that is the definition of our flash calculation, which is basically we have a separation process that happens between, and so our feed gets separated into the vapor and the liquid, and then the unknowns here are what is the amount that is going to be in the vapor phase, what is the amount that's going to be in the liquid phase, and then what is the composition of both of those phases. So that is what our flash calculation is asking. And we have, in this particular case, we have a given temperature, and a given temperature we'll say is 360 Kelvin, and then we also have a given pressure, which we'll say is 120,000 pascals. And what we could say, if we wanted to, would be how do we regulate the temperature? Well, we would have a cooling jacket to help us regulate the temperature for the flash drum, and then we would be able to say, how do we regulate the pressure? Well, we would have little valves, and let me get a little valve here, and so we could have our flow restriction valves, and so we can have a pressure drop across the valve, meaning we can have a higher pressure on the front end of the valve. So those are just ways that we can regulate our temperature and pressure to where we want it. And in this case, we're gonna know our given temperature, we're gonna know our given pressure, we know what our feed composition is going to be with our benzene and our toluene. And so what is known here is our feed, the feed composition, and what is unknown is the amount that is going to be leaving in the vapor phase, the amount in the liquid phase, the mole fraction amount in the liquid phase, then what we also don't know is the mole fraction so the composition now, right? So the mole fraction in the liquid phase, the mole fraction of each component. So this is of each component. We want to know what is the liquid phase, the mole fraction of benzene, for example, in the liquid phase, and then the mole fraction in the vapor phase for benzene, and also the same thing for toluene. And if we were dealing with more than just binary systems, we could have X amount or N amount of components that we want. We have as many amount of components as we want. In this case, we're just going to be dealing with benzene and toluene. But these are also unknown. And so what we see here is that we have 4 equations and 4 unknowns, which leads us to then ask, how do we go about solving this and moving forward? And that is going to lead us to unpacking, going back to Raoult's law. So we're going to also just consider that this situation is ideal and thus works for Raoult's law. Let's put that over here. Raoult's law, again, this is the mole fraction in the liquid phase, and its pure component vapor pressure, and that is equal to the mole fraction in the vapor phase multiplied by the total pressure of the system, which again, this, just to go back from the previous video, is the partial pressure for that particular component, benzene or toluene or whatever component that we're dealing with. And this is going to allow us to then look and consider xi and yi as a ratio of each other. And here's where we're going with this. So if we call the ratio between the vapor and liquid components the mole fractions of both of those phases, the ratio that we'll call is Ki, in which case we will have Yi divided by Xi. Now this equals the pure component vapor pressure for each component divided by the total pressure. Now the really cool thing about this is that if we have our temperature being known, if we know our temperature, which in this case we do, we're calling it 360 Kelvin, this allows us to, through the Antoine equation, and what we've solved in the previous videos, it allows us to know what our pure component vapor pressure is for each of our components. And also then the sum of the partial pressures lets us get to the total pressure of the system. And the really cool thing then about this is, for this, even if we don't know the mole fraction in the vapor phase or the mole fraction in the liquid phase individually, we don't know them individually, we can know what the ratio of them is, because we know this, because we know the temperature, which means knowing the ratio of this is going to come in really handy for the Rachford-Rice equation, which is what we're going to then move forward with now. So the Rachford-Rice equation, let's go ahead and write this out. Now, to start off in its simplest, is that we say the sum of the mole fraction in the vapor phase minus the sum of the mole fractions in the liquid phase equals 0. Or another way we could say it would be the sum of y1 minus x, or yi minus xi equals 0. So now we need to be able to say, how do we move forward from this part of the equation with what we do know with our temperature and our pressure and our feed to be able to solve our 4 unknowns, which is the amount of vapor, the amount that's in the vapor phase, the amount that's in the liquid phase, and the composition of each. So the xi and the yi. And so now let's start by setting our material and energy balance. And if we go back to this right here, we can see that we know our we know our feed, and we know, well, we don't know, but what we do know is that these two things are leaving the system. So we have our F, we have our feed, we have our vapor that is leaving, and we have our liquid that is leaving. So what's coming in is the feed, what's going out is the vapor and the liquid. Let's go ahead and express that here. So F equals V plus L. Now we need to be able to express this and balance this out with the components involved. So the feed is the feed of the composition makeup. So in this case, we got the 0.4 of benzene and the 0.6 of toluene as our mole fractions, adding up to 1 there. And then the amount that's going to be in the vapor phase, right? So whatever the mole amount, whatever the mole fraction amount is that is going to be in the vapor phase, we have to then also multiply that by the mole fraction of each component, benzene and toluene, that's going to be in the vapor phase. And then the same concept for liquid. It's going to be the amount of mole fractions, the amount of moles that are leaving as liquid in the liquid phase, multiplied by each component, benzene and toluene in this case, that are going to be in the liquid phase. So that is our Xi. Then we can go back to this equation here, and we can say, well, we can set things in terms of, let's see, sorry, right here. We can set this in terms of yi, because then we can use that as a substitution, meaning we can say that yi equals ki, so the ratio of them, multiplied by xi, because we can then take that in and substitute that into this equation right here. And let's go ahead and do that now. So we have now the sum of, let's see here, that's going to be ki and xi. That's substituting in what we just did on this right here. And that is going to be minusing xi, and that equals 0. So let's just go ahead and bring out the xi. So that is ki minus 1 equals 0. Now, what we can do to move forward from this step is we want to be able to express our component liquid, well, our mole fraction in the liquid phase, so xi. We want to be able to express that in terms of our zi, because we know the feed and we know the composition of the feed that is coming in, and xi is what we don't know. So let's go ahead and do that, which allows us to say from this equation here, we can be able to set this in terms of our xi, meaning we can go over here and say that the feed equals, now we can again substitute in yi, we know is ki, the product between ki and xi, plus, now with the liquid, what is the liquid phase? Well, another way we could express that would be the feed minus whatever is coming out as vapor. That's going to be what is left as our liquid. So the feed minus the vapor, mole fraction amount of vapor, well, that is going to be whatever's left is going to be leaving as liquid. So we can express that as F minus V, and that is multiplied by our xi. So let's go ahead and simplify that down. Bring out the x. So we have our V ki multiplied by ki. Kind of looks like I'm doing that as a subset, but that's not true. It's just the product between them. Let's make that a little bit more clear here. There we go. And then plus our F minus V. Okay, now let's just go ahead and divide this side right here. This right here. So xi equals the feed divided by, almost did it again, F minus V equals our xi. So now let's go ahead and divide across by our our feed. Let's see here. So we're going to divide by our feed here, cross by f. Okay, run out of space here. Let's go ahead and carry this equation into the next page. Let's go ahead and rewrite this so we can keep track of all of it. Wait a second, what did I write here? Yes, okay. Let's carry this out real quick also as I'm gonna carry the v out when I write it here. So this is with the v carried out, just to simplify things further. Now let's go ahead and divide across by f, which leads us with our Zi, our composition of our feed coming in between the benzene and the toluene, adding up to 1 for the mole fractions. So then that's going to give us, let's see, divided by our feed is 1 plus V over F multiplied by our ratio between our vapor and liquid composition, and then minus 1. Okay, now let's see here. Now the really cool thing is let's take a pause and just evaluate what it is that we know and what it is that we don't know currently at this point. So we know our our Zi composition. In this case, we got our 0.4 of benzene. We have our 0.6 as toluene. So we know our Zi. We know our feed flow going in. We know the composition, I should say. We know that whether it's going to be 100% vapor, 100% liquid, or some sort of combination between. So this is also known. And then we don't know yi and xi individually, but we do know ki based off what we expressed earlier, be it by knowing the known temperature through the end-to-end equation, knowing our pure component vapor pressure divided by the sum of the partial pressures added up to the total pressure of the system. So that is also equal to our Ki, which is the ratio between the mole component, or the mole composition in the vapor phase versus the liquid over the vapor phase. Vapor phase over the liquid phase. And so that is our Ki, which is known. And so that just leads us with not knowing our, at least on this side of the equation, well, we don't know our xi yet, but that just leads us on this side of the equation is not knowing what the mole fraction amount is going to be in our vapor that's leaving the system. And so what we can then do is just substitute our xi into the equation we've already been developing, because then that's just going to leave us with our one unknown to solve for. So let's go ahead and carry out the equation that we're going to be doing. And up to this point, what we have done is, let's see, where are we at? We are right there. It is. Okay. With all the equations kind of lost the bearing. So let's go ahead and rewrite this on our page here. So the sum of xi multiplied by, okay, the sum of xi multiplied by ki minus 1 equals 0. So now we can just go ahead and substitute this into here, because this equals, this is xi. So now we can express this and say that from whatever our from I equaling 1 all the way up to z components, or we could say n, or we could say z, but basically n components. So we could have x amount, z amount of components we want, 3, 4, 5, 6, whatever, but in this case we're just doing binary. So this will say just as benzene and toluene. And then so the sum from some of those from I all the way up to the total amount that we have is, and then substituting this in, is just Zi multiplied by Ki minus 1. All of this is over 1 plus V over F multiplied by Ki minus 1, and this equals 0. And so now we know our feed composition mixture amount right here. We know our ratio by knowing our given temperature. We know our feed, and then the only thing we don't know is V, and so now we are able to solve for the vapor that is going to be leaving our system. And so this right here, this is a little sloppy, let's just take that out. This right here is our Rachford-Rice equation that is derived for our flash calculation, which again is dealing with the flash drum, where we have a separation process between vapor and liquid that is separating between those two components, two phases, I should say, and then being able to ask what are our 4 unknowns, and this boils us down to be able to work with our one unknown now through the Rachford-Rice equation and saying, what can we do now to solve for how much of the mole fraction is going to be leaving in the vapor phase, which allows us to move forward with the rest of the unknowns. Thank you for watching, and then we'll progress forward and go ahead and code this out in Python and be able to see what each of these values are going to be with this as our mole fraction amount coming in, or our mixture composition coming in through our feed, and then getting separated out into the various phases, and what that's all going to look like in its exact amounts in the next video. Thanks for watching.